Alright, so this is another video on double integrals, and in this one we're going to continue with some more examples, but look at some different types of examples. Here in this first example that you see is one of the applications of double integrals, which is actually double integrals helping calculate volumes. So basically, as we're asked here, we're asked to calculate the volume of the tetrahedron bounded by the planes x plus 2y plus z equals 2, x equals 2y, and x equals 0 and z equals 0. Now, of course, the best scenario is that you draw or try to visualize this tetrahedron. So a tetrahedron, by the way, is like a prismic kind of a figure, which is more like a some form of three-dimensional triangle. So what you need to understand here is that, as I've said before, now I'll show you the diagram a little later, but let's try to solve it without drawing anything so that you don't, when you see me put a diagram up here, you might think that, okay, well, it's easy for you to put up a diagram. How am I supposed to solve the question? Don't get into that. Let's not draw anything and just try to visualize what is actually happening. So when we say we have a tetrahedron, let's go easy. Don't go with this plane first. Let's go with the easier planes. So we've got a x equals 0 and a z equals 0. So if I were to quickly draw, which everyone should be able to draw, our axes. So this is your y-axis, your x, and your z-axis. So what's going on is z equals 0 means this is your xy plane. So your bottom is somewhere here. So it's bounded at the bottom by z equals 0. Now on the other hand, so everything is above this z equals 0 plane. So you still have this side and you have this side of the xy plane, but nothing below. So the below is cancelled. So there's nothing below in the negative part of the z-axis. Now x equals 0, bounded by x equals 0. Now x equals 0 is the plane that is along yz. So it's this plane. It's this plane all along here. Now, and of course it won't go below the z-axis. So it's this plane that's bounding it. So now we've got x equals 0 and z equals 0 bounding this plane. So basically you're looking at something like this so far. So these are your two planes. Now this is not so difficult to visualize or draw. As you can see, my drawing is lovely. But anyway, so it's above and x equals 0. Now the issue is x equals 0 doesn't actually tell you where the bound is. I mean, you could be on the back of this or on this side of this. It doesn't clearly tell you that. That's why we need the other planes. So x equals 2y. Let's look at that. So here, now you'll see the x equals 2y. So x equals 2y, just think of this as over here as x equals 2y. So it's going to be some line here. Now the line means z is free. So remember, this means it's a plane. What's going to happen is you're going to have this plane all along here and, going up as well. Okay, so it's all along here. So this is so it's going to be like this kind of a plane. Okay, so it's going to be like that. Now you can see that it's starting to close up a bit of the area. So clearly, I'm going to use red now. This area is no longer included. So the red is not included. Okay, this is not included. So what's being enclosed seems to be here in yellow. I'll put up here. So what's happening is that's one plane. This is another one. So it's between these two. So you can see that there's the tetrahedron is starting to appear. Okay. So let's now look at the final one. And the final one is the cider one. This is x plus 2y plus z equals 2. Now what this is telling me is that, in fact, there is some kind of a plane that is intersecting y. So we have x0 and z0, which means y equals 1. So we have a point here. So there's your point 0, 1, 0. Okay, so we have one point here, and then we have another point. This plane actually will go up here and intersect somewhere on the z-axis. So that happens when x and y are both 0. So when x and y are both 0, you get z equals 2. So we have 0, 0, 2. Now that should be sufficient for you to understand that there is some form of this plane is somehow this type of plane. Okay, So that's what's going on here. So this is a slanted plane like this. Now once you do see that, immediately what should happen is you will notice that now you have your tetrahedron, which is somewhere in the middle of these, and closed down here. So you have in fact a tetrahedron. Now of course that doesn't look very nice. Let me clean that up a little bit. Much cleaner, as you can see. Looks much more like a tetrahedron. Again, this is taken from Stewart's calculus. Let me just put that here. This is Stewart's calculus. Okay, just for your reference. Now, now you can clearly see what area we're looking at, or what we're trying to find the volume of. Now let's go to try to set up this integral. So now, by the way, as I told you, you need this only to visualize. You don't have to have the diagram. You can do it completely without the diagram by just looking at what situation we are in, which is essentially the following. If you look at our x equals 0 and z equals, from this top plane here, what we can see is that z is equal to 2 minus x minus 2y. Okay, so your integral, remember, double integral is like this, and there is a function z over which you're going to be integrating. So your z is going to be that. Okay, that's the first thing you need to keep in mind. Now we need two ranges, these two ranges, and these will be of x and y. In order to do that, we'll have to start substituting in and start looking for intersection points. And what that means is we'll start by looking at, in fact, we're looking at substituting z equal to 0 in here. Okay, will give us that x plus 2y equals 2. Okay, which means that y is equal to 1 minus x over 2. Okay, so that's what we get, 1 minus x over 2. So now we've got, in fact, that's a line. And once we have that, then you can easily go into a 2D drawing, even if you, obviously you can't, I'm not expecting you to be able to draw the diagram you see on the right here. But what you can do, on the other hand, is you are able to draw 1 minus x over 2. And the other thing you have here is from the other equation, from this one, we see that y is equal to x over 2. Okay, so this means if I were to do this in a 2D, here's your x and here's the y, clearly we have the line y equals x over 2, which is going something like this. All right, and we have the intersection point of these two lines, which is going to be at, since they're going to be equal, we're going to get x is equal to 1. Okay, so they're going to intersect at x equals 1. So at x equals 1, so that means this here should be 1, and the value when x is equal to 1, both of these are going to be a half. So here's your half, this is a half, so there's that point. And of course this line, when x is equal to 0, is going to give you 1. So approximately here. So these are the two lines. So basically you've got this. This is a piece of cake. You should be able to do this quite easily. And clearly, since I've shown you this is x over 2 and this is 1 minus x over 2, that clearly tells you that your lower range for values of y, so your y is going from x over 2 to 1 minus x over 2. Okay, and we already have our range of values of x from, of course, 0 to 1. And since we have these, we are now in a position to do our double integral. So our double integral now forms as follows. It'll be the x range 0 to 1, the y range from x over 2 to 1 minus x over 2. Okay, and it's going to be so here we have the z function, which is 2 minus x minus 2y, and of course we're doing y first and then x. Okay, so I'm sorry I took a little long there, but just I wanted to get you to understand how we calculate these volumes and different ways of calculating these. All right, now I'm going to skip the details and just show you this much only, that the integral will boil down to just x squared minus 2x plus 1 dx from 0 to 1. And when you solve that, it'll be 1/3. Remember, my interest here is the integration should be simple for anyone at this level now, hopefully. But the main thing is the setting up of this integral. So this integral, okay, is our key to this problem. Okay, so hopefully you get that. So we have basically, let's look at this example. So d xy dA, d is bounded by -1, x minus 1, and 2 y squared equals 2x plus 1. So basically what we end up with this is best ways to do this as a type 1, or sorry, type 2 region, which means x is equal to y plus 1, and then x is equal to half y squared, okay, minus 3. Okay, so this is now the only thing you have to figure out is which region is to the left and which region is to the right. In order to do that, the first thing you should do is look for the intersection point. So you should look at y plus 1 is equal to half y squared minus 3, which gives us a quadratic, in fact. So we end up with, so we'll have this quadratic, which basically tells us that this is a factorization. So y equals 4 and y equals minus 2. Now if that's the case, that gives us the intersection point. This one gives us x is equal to 5, and this one gives us x is equal to minus 1. So basically our two intersection points are 5, 4, and minus 1, minus 2. Okay, so that is important because that'll give us the range of values that we're looking for. So your now, and that also tells us the values we can use to test. So the range of values of x, the range of values of y are going from -2 to 4. So your y is between -2 and 4. Okay, so y is between -2 and 4. Now if y is between -2 and 4, let's test a value. Both our functions are going to be increasing in this range. So I mean, it's so that means if you choose a value like, for instance, y equals 0, that tells you that here x is 1. This will be x is equal to 1, and this one will give you -3, which means the y plus 1 is further is more in value, which means it is towards the right. So therefore you have your x range. So your x is going to be between half y squared minus 3 and y plus 1. Now this is without drawing. Now if you were to draw this, which probably is the best thing to do, you'll have this sort of situation. This is somewhere here, -1, -2. Okay, so this is 1, this is -2. All right, and it's going to be here, we'll say, is our 5, 4 intersection point. And the curve is going to go something like that. So that's what we're looking at, and we're going from right to left. Always remember, left towards right. So the one that's to the left is the lower bound of the integral, and the one to the right, the curve to the right, is the upper bound of the integral, upper value. So essentially this means that you have -2 to 4, and then you have, of course, half y squared minus 3, and this is going all the way up to y plus 1. All right, and we are integrating xy, and we're going to do this time dx first, and then followed by dy. And of course that will be equal to, so that's going to be equal to that, which will work out in the end to be 36. Okay, so we'll stop here.